Hello everyone, my name is Wen Han. You can also call me Jack. I'm an engineer from Multicoreware. And today I'm going to tell you a little bit about our experiences to implement C++ AMP on Opencl as well as HSA. So first, let me do a quick introduction of our company. I'm from Multicoreware. The company was founded in 2009, and we have offices around the world, and we've got like maybe 200 people in total. So I think we're the largest independent Opencl team in the world. So we provide software tools and software acceleration services for our customers. And what I am going to talk about today is about C++ AMP, and Dr. Wenmei Hu, who is our CTO, and he championed this project. So my agenda today is to first give you a quick introduction of what C++ AMP is, and we'll talk about our implementation, which originally it was called Clang, but recently we changed the name to Kalmar, which is a small town in Sweden. And we'll show a bit about how to implement this on Opencl, and after that we'll do some case studies, and we'll also talk about a bit on how to run C++ AMP on HSA, because HSA has some unique features, so we can make the code more simple, more elegant. And finally, because we have this C++ AMP implementation, so based on the functional blocks we have in place, we can actually work towards more generic C++ codes in the coming future. So I would like to show you a bit a simple example of what C++ AMP is. So this is a very simple matrix multiplication algorithm written in C++ AMP. So we want to multiply A matrix with B matrix and save the data, the result into product matrix. So in C++ AMP, we first have to model this data into certain data container objects called array view. So we tell C++ AMP runtime that these guys will be transferred into GPU memory later on to do the computation. And in C++ AMP, there's an interface called parallel for each, and which marks a region where codes inside this region will be executed parallelly on GPU. And the code actually be executed on GPU is modeled as a C++11 lambda function. And in Opencl, we have to, when we write kernel functions, we have to specify the kernel arguments. But in C++ AMP, we don't need to do that anymore. These kernel arguments will be can be used directly within the kernel functions. So they are modeled as C++ so-called captured variables, in the lambda function. And after the computation is done, we can use a synchronized method, or we can use RAI style to make sure the data are sent back to host memory. So this is a very simple example of C++ AMP. And compared to other technologies such as Opencl or CUDA, this is a single source programming model where host codes and kernel codes lie in the same file. In comparison, it's in the same translation unit. So how do we implement C++ AMP on Opencl? So basically, we have, based on Clang and LLVM compiler infrastructure to create this implementation. And originally, we started from like LLVM 3.1, but when the stuff get matured, we were sitting on 3.3, and that's where the main repository is using right now. And we already have a 3.5 port, and we are hoping to upstream our works back to the community pretty soon, so it will always keep up with the latest version of Clang and LLVM. So we can, this Kalma compiler, we can lower C++ codes to different GPU targets, such as Opencl SPIR binary, or Opencl C, or HSA, the HCL or source format or brick binary format. And we can also generate x86 codes as a CPU fallback, so you don't really need to have an actual GPU to run C++. And we have tested on all major Opencl stacks, and so far things looks fine. And of course, we support HSA as well. And if you guys are interested, please go to Bitbucket, where we host all the codes there. So in this figure, I show the build process of our compiler. So when you supply a C++ source code into Kalma compiler, first the compiler driver will be triggered, and unlike normal C++ compiler where you will just start compilation on CPU, the driver will actually invoke two different compilation paths. So the first one is to build kernel codes, and the second one is to build host codes. So building host codes are much more simple, so we won't discuss them today. And we'll talk a little bit more about device code compilation, where we take the kernel part of C++ AMP and compile into GPU kernels. So let's take a look about the most important steps in compiling device codes. So because we all want to run full C++ on GPU, but unfortunately that's not available at this moment, because there are quite a few features in C++ which are very hard to be implemented on GPU. So we changed the Clang compiler front end to enforce some additional rules which are not available on GPU. And also in the example we showed previously, that in kernel codes in C++, you don't have to manually specify kernel arguments now. So the compiler will need to do the work. We need to turn these captured variables into Opencl arguments. And say if you capture like a large object, a custom user-defined C++ object, then the compiler will help you flatten it out into a list of primitive Opencl kernel arguments. And also, I forgot to mention that because in C++, lambda functions are there's no name associated in the lambda function. So how do we distinguish between different kernels? So compiler need to do some work to name those unnamed functions. So we need to correctly construct kernel function prototypes, so host codes can correctly locate which kernel to execute. And there are also some more in-depth stuff where we need to deserialize all the kernel arguments and reconstruct them into objects on GPU memory. And also because the kernel will be running on many different work items on GPU, so the compiler need to correctly populate work item index in the kernel codes. Okay, so in this slide we talk about major steps in device side, device code compilation, and to actually lower the codes for different GPU platforms, there are some additional steps need to be done. So in C++ AMP, there's no notion for memory address spaces. well, there's a title index stuff where it's more or less the same as local memory in Opencl jargon, but in general, when you program in C++amp, you don't need to specify where the address space is. So the compiler need to do the work for programmers. We need to deduce the memory address space for kernel arguments. And then we need to link with different platform-specific built-in functions, such as atomic functions, floating point functions, and work item indexing functions, because these functions, they all have different signatures or prototypes on Opencl or HSA. And then we will do some inlining and optimization for different GPU targets, and then produce SPIR binary or OpenCLC or HCL brick format. So the way we produce OpenCLC is to produce SPIR binary first, and then we change the C backend from LLVM. So we take the SPIR binary, which is like a special form of LLVM IR, and then we use this modified C backend to emit OpenCLC source code from SPIR. And to produce HSA brick or HCL format, our compiler depends on the HCL compiler from HSA Foundation. Yes?
How do you decide the global variable, local variable, or do you do anything for latency hiding? If you just put everything in one big function, it's going to be like data transfer time, execution time, data transfer time.
Uh-huh.
All these three things are packed into one, right? Is that how you do that?
So in C++amp, there is a special keyword called tile static, where you explicitly specify that a buffer should be stored in local memory. Yeah. And if not, then we will put everything in global memory address space.
But the data transfer penalty would still be there. So do you do anything for data transfer?
Oh, okay, I see. I got what you mean. So in C++amp, there are two kinds of data container objects. One is called array, and the other is called array view. And normally, if you say if you got a buffer which will be which you would like to store it on device memory and run quite a few kernels and to access that buffer, you will use the array data container. So the data will stay on GPU until you use some synchronized method to copy it back.
You're separating the data transfer from kernel.
Yeah, that is right. Okay, so here I show you a conceptual compilation of device code. Actually, so here is a very simple matrix multiplication algorithm, and here this is the conceptual compiled OpenCLC. Actually, the actual compiled OpenCLC code will be much more ugly, yeah, because there are some more details in the implementation side. So let's take a look of what I said earlier. So for this input A, matrix A, B, and product, they are array view objects. And so the compiler will take these captured variables and then flatten them out into kernel arguments here. So, so for example, this VP, row P, and col P, they are members inside product, so they will be flattened out as kernel arguments. And also, the compiler will deduce that, okay, this integer pointer should be stored in the global memory segment. And yeah, that's a conceptual compilation. And once we have compiled the host codes and device codes, and we'll link everything together as a binary executable, and also we will have a small platform-neutral C++ runtime linked with the executable. And this runtime will lazily determine which platform-dependent runtime is available on the system and pick the correct one and dynamically load and delegate all platform-dependent codes to actually execute to use the GPU. So in the previous presentation, there was some discussion about CO+, right? So we feel that CO+ is actually pretty good, but we have optimized. So we have rewritten CO+ in C++M, and we see some very good improvement in various input parameters to the SGEM function. So that's one use case using our Kelma C++M compiler. And we are also working on deep. Sorry?
Are those the results of running Opencl that comes out of C++M, or is that?
Yeah, yeah. This column is the average running time of Opencl codes coming out of our C++M compiler.
And do you have explanation for one, the iteration result? There's like 1,100 row.
Sorry?
There is like one where you have decrease in performance. One row is about like 7 from the bottom.
I'm sorry.
Maybe in the interest of time, we'll take that one offline and come back later on.
Mm-hmm. Okay. Yeah, and we are also working on deep neural networks as an application of C++M. So with Torch 7, we have implemented a C++M backend, and with the same training data set and with some comparable hardware configurations, we're seeing some improvements in our C++M, using our C++M based backend. And yeah, and let's do a quick introduction of HSA. So we know that on HSA and also Opencl 2.0, there are shared virtual memory. So we can leverage them. So we don't really need the array view instances, and we don't really need to do the synchronization. So on HSA, codes can be much more simpler. And we can just directly use the pointers on host memory to do computation. So there's no need to do explicit creation of CO buffers and move things around. And also on HSA, there's another feature called platform atomics. So we can do lock-free synchronization between CPU and GPU thanks to the memory order in C++11. And yeah. So we have implemented a Kelma compiler, which currently could take C++M. But the same building blocks in place can be used to implement other parallel programming paradigms as well. So currently we are implementing some proposals to C++17, which are also related to parallel programming. So we are implementing them, and we hope to make them publicly available in the next quarter. And we would like to also try to allow more C++ syntax in GPU kernels, as well as supporting SPIR-V, and also upstream our stuff back to Clang and LLVM community. So that's all for my presentation. I'd like to take questions from you guys. Thank you.
So let's thank our speaker. Thank you, Jack. And maybe if you want to get yourself ready. So while we're just switching speakers, there's time for maybe one question. Yeah, I'll come.
So when you say you allow more C++ syntax, what are the restrictions and how are they going to get relaxed? So what are you going to relax there?
Okay, I think one of the most important restriction we have here right now is the virtual function calls. So for virtual function calls, you need to look up the V table and so on to reference where the address of the actual function member function is. So right now it is not possible at this moment, but we're trying to implement that. So I believe that is the most fundamental problem we want to attack.
Okay, thank you. Let's thank our speaker again. Thanks, Jack.